quick recap of what we have been discussing in last class. So the problem that we have is we have x1, x2, xn, a random sample from normal mu sigma square. And what do we want to do? We want to estimate or guess the unknown parameters mu and sigma square. Not only we want to estimate, but we want to understand certain statistical properties also of these estimators. Okay, so there are two things, estimators and estimate. In real life, what do we observe? In real life, we do not observe random variables x1, x2, xn, but rather we observe the realizations of these random variables x1, x2, xn. So those realizations are actually nothing but the data we call nowadays, we call it data or a random sample again, right? I'm using the notation. So all these things are, I hope, clear to all of you. You have revised. And then the objective in the last class that we were trying to set up was we want to estimate sigma square, right? So there were two choices of estimators for sigma square. One was written here as t and the other one is written here as s square. So s square notation is universal, right? Whenever somebody says sample sample variance, you have to look at this particular choice, right? So this is what you have: a square 1 upon n minus 1 sigma I from 1 to n xi minus x bar whole square, right? So this is the sample variance, and we proved that s square is an unbiased estimator of sigma square. That is, expectation of s square is sigma square, we proved. And we also proved that t, the estimator t, actually underestimates the sigma square, right? And we found out distribution of n minus 1 s square by sigma square, and the distribution of that n minus 1 s square by sigma square turned out to be a chi-squared density with n minus 1 degrees of freedom. And this chi-squared density is basically a special case of gamma density, right? So the gamma density with gamma n by 2 half is basically chi-square n, right? And once you know what is gamma density, then from gamma density you could do all these things and we could prove. So this was an important fact that we had, that x square and x bar and s square are independent of each other, right? So these are the things that are independent of each other. This is something that I have not proved, but if there is time today I will prove it. Otherwise you have to accept it as a fact, okay, that x bar and s square, they are independent random variables. And using this fact, we actually proved that this n minus 1 s square by sigma square actually follows chi-square density with n minus 1 degrees of freedom. Okay, so this is what we have done so far. So let us continue our discussion further. So what we have done, previously done. Okay, what is it that we have done previously? So the case one that we have done is x1, x2 up to xn. So this x1, x2 up to xn is IID normal mu sigma square. Okay, consider the case mu is unknown, sigma square is known. Okay, then in order to estimate mu, x bar was used, right? X bar as an estimator of mu, and there was a random variable z we called, which was x bar minus mu divided by sigma by root n, and we know that this random variable follows normal density with zero mean and variance 1. So basically what we know is x bar follows normal density with mu sigma square by n, right? So this is something that we already know. Here mu is unknown parameter, but this sigma square by n is known, right? Sigma is known, so sigma square n is known, right? So this was something that we looked at. The second case that we looked at was that x1, x2, xn actually is a random sample from normal mu sigma square. Okay, and we wanted to estimate sigma square. This is what we did in yesterday's class. We showed that expectation of s square is sigma square. So s square is an unbiased estimator. And we showed that n minus 1 s square by sigma square actually follows a chi-square density with n minus 1 degrees of freedom, right? This is something that we have actually showed yesterday. And now today we want to see the case. the case that we want to study, is that sigma square is also unknown. Okay, so sigma square is also unknown, mu is also unknown. Then x bar obviously will still be an unbiased estimator of mu, but a random variable like z, what will be the density, right? Here, what will be the density? So if I replace this sigma, by s, right? S being the, I am estimating the variance by s square. So s being the positive square root of s square, okay, which is an estimate of sigma. Okay, so if I substitute this estimate of sigma here in Z, what is the density that I'll get? That's the question basically I am asking. Okay, so that's the question I'm asking, and that question will be answered by something that we are going to do today. We are going to do the T distribution. Okay, so that's what we are going to do. But before we go any further, in the case one that we had seen yesterday, that x1 up to xn is random sample, normal mu sigma square, mu unknown, sigma square known, let us say for example, sigma square known. Then we have seen that z is equal to x bar minus mu divided by sigma by root n. This z follows normal 0, 1. We had seen that yesterday. And suppose this is 0, this is the PDF of normal 0, 1. Okay. So if this is the PDF of z, which follows normal 0, 1, so standard normal density, then last time in the last class we said that we will call this point to be z alpha by 2. So what is the property? The property is that this particular area to the right of this point is so so z greater than z alpha by 2 is actually equal to alpha by 2, right? So that is what we decided. So we pick a number alpha between 0 to 1, and this is how we define this point z alpha by 2. So this point is generally called as percent point. Okay, so these are percent points. And because of the symmetry of this distribution, if you consider minus z alpha by 2, then this area is also alpha by 2, right? So this is something that follows because of the symmetry. And then whatever is the area which is remaining in between, is actually 1 minus alpha. And then we wrote a probability statement yesterday. What was the probability statement? Minus z alpha by 2 less than less than the random variable. So the random variable capital Z, which take values between minus Z alpha by 2 to Z alpha by 2, this is actually 1 minus alpha, which is basically same as probability minus Z alpha by 2 less than X bar minus mu divided by sigma by root n less than Z alpha by 2 is equal to 1 minus alpha, right? And if I simplify this, then what do I really get? You check, is basically x bar minus z alpha by 2 sigma by root n less than mu less than x bar plus z alpha by 2 sigma by root n is equal to 1 minus alpha. Is that okay? And here I define this L to be x bar minus z alpha by 2 sigma by root n, and u I define to be x bar plus z alpha by 2 sigma by root n, right? And I consider this interval LU. So this particular interval LU is such that unknown parameter mu lies in this interval. What is the probability that this unknown parameter mu lies inside this interval LU? That probability is given by 1 minus alpha. So if you start with alpha is equal to, let us say, 0.1. Okay, so if you start with alpha is equal to 0.1, then you will find out from the normal table this z alpha by 2. What is the value of z alpha by 2? I think this value of z alpha by 2 in this particular case z 0.05 is 1.65. Okay, so this value is 1.65. You can check this from normal table, make sure. And once you have this value, then you know sigma also, you know sigma also. Sigma is known. That is the case that we have considered. You know the random sample size, then you can actually calculate L and U based on data, right? So what is based on data? What is based on data is this particular value of X bar, right? So based on data, you can actually calculate the values of L and U. And once you calculate the values of L and U, then you have an interval rather than a point, right? Earlier, what we had said, earlier we had given a point estimate, the value of X bar, whatever is the realization of X bar, that is what we had given. Now you are giving out a confidence interval, so to speak. You are giving out an interval and you are saying that you are 90% sure 1 minus alpha is 0.9. So you are saying you are 90% sure, you are 90% confident that the true value of the parameter mu lies inside this interval L and U. And how will you compute L and U? So this particular guy is U, this particular guy is L, and you can see from the data and from the given information, everything is available, right? So you can compute L, you can compute U from the data, and once you compute L and U from the data, then you can compute what is the confidence interval. So this is something that is called as interval estimation. This is something which is called as interval estimation. In this, what you really do is you are, instead of giving a point estimate, you are giving an interval as the estimate. Okay, so interval is an estimate. That is what you are really giving. So this is this is what you are really doing. Okay, so similarly, if you consider the next stage, if you consider the next step, then case 2. So what is happening in case 2? So x1, x2, xn is actually IID normal mu sigma square. Okay, IID normal mu sigma square. And what do we want to do? We want to estimate sigma square. So we want to estimate sigma square. That is the problem that we have at our hand. And we consider S square unbiased estimator of sigma square. And what do we know? We know that n minus 1 S square by sigma square follows chi square with n minus 1 degrees of freedom, right? So n minus 1 S square by sigma square follows chi square with n minus 1 degrees of freedom. This is what we know. So the way chi square density with n minus 1 degrees of freedom really look like. So suppose this is the graph, okay? So this is the PDF. This is the PDF of random variable n minus 1 S square by sigma square, which follows chi square density with n minus 1 degrees of freedom. Okay, so this is something that we have already proved, right? And this is the PDF. The PDF looks like gamma. We already know that the support is only 0 to infinity. So the density will look like this. And again, in this density, what I really do is I find out 2 points. Okay, so I find out 2 points. So I fix alpha in 0 to 1. And once I fix alpha in 0 to 1, I find out this point, chi square. So let me write it down clearly. So chi square n minus 1 alpha by 2. Okay, so what is this point? This point is really saying that to the right of this point, the probability is alpha by 2. Correct? Similarly, I can find out a point. I can find out a point, but now this point is really very critical, right? So this point is such that chi square n minus 1, and now I have 1 minus alpha by 2, right? So what is 1 minus alpha by 2? The probability to the right is 1 minus alpha by 2. That means that probability to the left is alpha by 2, right? Because of non-symmetry now here, because of non-symmetry here, the notation is a little different. And what happens? What happens is that in this particular range between these 2 points, this particular probability is 1 minus alpha. And then you can again write down the probability statement the way we wrote down. So the probability that this particular point, chi square percent point 1 minus alpha by 2 less than or equal to n minus 1 S square by sigma square is less than or equal to chi square n minus 1 alpha by 2 is equal to 1 minus alpha, right? That is the probability statement that we will write. Now sigma square is unknown. All other things are known, because these things like normal density, you can find out these points from the table, chi square table. And once you find those things from chi-square table, then you can write this thing down. So probability, now I'll reverse the inequalities because I'm taking the inverse ratio. So chi-square n minus 1, 1 minus alpha by 2 greater than or equal to sigma square n minus 1 s square greater than or equal to 1 by chi-square n minus 1 alpha by 2 is equal to 1 minus alpha, right? And then by readjusting the terms, you have n minus 1 s square divided by chi-square n minus 1 alpha by 2 less than or equal to sigma square less than or equal to n minus 1 s square divided by chi-square n minus 1 1 minus alpha by 2 is equal to 1 minus alpha. And then again in this case you are saying that you have 1 minus alpha times 100% confidence, right? So if you take alpha is equal to 0.1, then you have 90% confidence. If you take alpha is equal to 0.05, then you have 0.95 probability that the true parameter sigma square will lie between these limits, right? So this is the lower limit and this is the upper limit, and the true parameter lies between these lower and upper limits. That probability is 1 minus alpha, right? So based on value of alpha that you choose, you can find out these chi-square percent points. You can find out, you already know a square because that you can compute from data. You know the sample size, so you know what is n minus 1, right? So this is something that we have. And the similar analysis, if you were to do in the case when sigma square were unknown, similar analysis if you were to do in the case when sigma square were unknown, then this particular random variable z cannot be used, right? Because here sigma is known, that is the assumption. With that assumption we are saying that it follows normal 0 1. But if sigma is not known, then what will we do? We'll use the estimate of sigma, which is nothing but s, the square root of s square, the sample variance. And if we use that, then we have a different random variable x bar minus mu divided by s by root n. And what is the density of that random variable? That is the question we are asking, and that's the question we will answer. Okay, so case 3. What is the case 3? Case 3 is that you have x1 up to xn random sample from normal mu sigma square. Now here mu and sigma square both are unknown. Mu sigma square both unknown. Okay. And what do we want to do? We want to estimate mu. Okay, estimate mu. So x bar is an unbiased estimator. Unbiased estimator of mu. Okay, this is fine. X bar is still unbiased estimator of mu. I think somebody is not on mute. Please make sure that you are on mute. Okay. So x bar is an unbiased estimator of mu. And what do we want to do? We want to understand the distribution of certain distributional properties of x bar, right? So since sigma is also unknown, consider the random variable x bar minus mu divided by s by root n. Okay, so what did we do? We replaced sigma square or sigma in z by s. Okay, estimate of sigma. Okay, so this is the estimate of sigma and we are replacing sigma by its estimate. Okay, s by root n. Then the question is, what is the density? What is the distribution? X bar minus mu divided by s by root n. Okay, so that is the question. What is the density of x bar minus mu divided by s by root n? So that is the question we are asking. If this s were equal to sigma, which is known, then we know that this is normal 0 1. But if this sigma is unknown, then we'll replace this sigma by s, the estimate of sigma. And if that is the case, then we will ask the question, what is the density of this particular random variable? So you can see that x bar minus mu divided by s by root n. I can actually write this down. X bar minus mu I can divide by sigma, and I can write this down by sigma by root n and s by sigma, which is basically nothing but x bar minus mu divided by sigma by root n and square root of s square by sigma square. Okay. And what do I have here? I have ratio of two random variables. So I will call this. So the ratio here is z, and here let us call this to be square root of some random variable. Okay, z1 and z2. Okay, so we already know that z1 follows normal 0 1. Okay, so we are looking at ratio of two random variables. And what are these two random variables? These two random variables is that z1 follows this, and we know that so this s square by sigma square. Okay, so this s square by sigma square we can write down as n minus 1 s square by sigma square into 1 upon n minus 1. Do you all agree? And this particular random variable follows chi-square with n minus 1. And then this particular z2, so maybe this notation is not clear, but z2, so if I call this z2 to be equal to n minus 1 s square by sigma square, then I have here z2 divided by n minus 1, right? So z2 divided by n minus 1 is s square by sigma square. So the given random variable x bar minus mu divided by s by root n. So this random variable actually is ratio of z1 divided by square root of z2 by n minus 1, where what happens? Z1 follows normal 0 1. Z2 follows chi-square with n minus 1 degrees of freedom, and Z1 and Z2 are independent. Z1 and Z2 are independent. This is important. Three conditions. Okay. So Z1 and Z2 are independent. Why are they independent? Because you have S square in the denominator, you have S square in the denominator, and you have X bar in the numerator. X bar and S square are independent of each other. That's the fact that we had stated yesterday, though we have not proved, but that's the fact that we have stated yesterday. So X bar and S square x bar and s square are independent. So numerator random variable z1 is independent of denominator random variable z2. So what do we have here? What do we have here is a ratio of a standard normal random density z1. So this is what I have in the numerator. So this is what I have. So this is my z1. And this is the square root of z2 divided by n minus 1. Okay, this is the square root of z2 divided by n minus 1. And basically this is ratio of normal 0 1. So by naively I will write down this is ratio of normal 0 1 divided by square root of chi-square p divided by p. Okay, so this is what I have, and numerator and denominator are independent. Okay, so numerator and denominator are independent. So if that is the condition, then I am interested in finding out the density of this particular random variable. Okay, this is what I am really interested in doing. I want to find out density of this random variable. So basically if I am able to find out density here, then I have found out density here where I can replace p by n minus 1, right? So the objective now, so the aim is now to compute the density. So let u be a normal 0 1 random variable, and let v be a chi-square random variable with p degrees of freedom. Okay, so this is with p degrees of freedom, and u and v are independent. Okay, u and v are independent. So if u and v are independent, then what am I going to do? I am interested in finding out, compute the density of this random variable. Which random variable? Compute the density of this random variable u divided by square root of v by p. Okay, so this is the random variable. So this is the transformation of u and v, and this is what I really want to compute. Okay, this is the density. That is what I want to compute. Okay, so first of all, the approach that I'm going to do, I'm going to take is the following. Okay, so let fu be the density of u. So it is a normal random variable. So what is the density? 1 upon root 2 pi e to the power minus u square by 2 for minus infinity less than u less than infinity, right? So this is the density of u. And similarly, what is the density of v? V is a chi-square p. So chi-square p is gamma p by 2 half. So that density we had already seen, half to the power p by 2 gamma p by 2, correct? Half to the power p by 2 gamma p by 2 e to the power minus v by 2 and v to the power p by 2 minus 1 for v between 0 to infinity and is equal to 0 otherwise, correct? This is the density of gamma, so I have just written down gamma p by 2 half, right? So that's what I have written down. So this is the density of this. So the joint density of u and v is what I am really interested in finding out. Okay, so let f of uv denote the joint density of u and v. Okay, joint density of u and v. So what is the joint density of u and v? Joint density of u and v I can write down as marginal densities product. Why can I write this down? Why can I write this down? Joint is product of marginals.
Side dependence.
Yeah, correct. I have assumed that u and v are independent. So here the independence is coming into the picture, right? So since u and v are independent, this is what is going to happen, right? So I can write this down. So let us write down this. So this is only a product. So f of u and v will be actually equal to 1 upon root 2 pi e to the power minus u square by 2. Then you have 1 upon gamma p by 2, 2 to the power p by 2. So 1 by 2 to the power p by 2 in the numerator I am writing in this particular form. E to the power minus v by 2 and v to the power p by 2 minus 1, correct? So I am just taking product of these two densities. This is what I am doing. And now what I'm really going to do is the transformation trick. Okay, so the transformation that I am interested in doing. So what is the density I want to find out? The density that I want to find out is this density, right? Density of this particular random variable. Okay, so the transformation that I am going to do is the following. Okay, so the transformation that I'm going to do is following. So what is the transformation? Transformation is that I want to find out density of this random variable. So let us denote it by t, which is nothing but u divided by v by p. And this is what I want. And the other random variable transformation I took is w is equal to v. Okay, so this is what we have. So what does that mean? That means that u is equal to t into square root of v by p, which is same as t into square root of w by p, which I will write down as t into w by p to the power half. Correct? So I am actually making the transformation u is equal to this, and I'm taking the transformation v is equal to w. So this is the transformation that I'm making. Okay, so the transformation I'm making is this transformation. So why did I make this transformation? I made this transformation because I want to find out density of t. So that's why I made this transformation. So this is what I have. U is equal to this, v is equal to this. And from here, you can see that the range of t will be minus infinity less than t less than infinity. And because w is equal to v is nothing but chi-square density, 0 less than w less than infinity, right? The range of w is this. And now what we want to do, we want to find out Jacobian. The Jacobian is what? Determinant of this particular matrix. So del u by del t, del u by del w, del v by del t, and del v by del w, correct? So this is the determinant that we want to find out. So this is the Jacobian of the transformation. So what is this? So this is actually equal to determinant of this matrix. So what is del u by del t? Del u by del t is actually w by p to the power half, correct? So this is the function t into w by p to the power half. So this is what we will get. Here, I will not really compute what is the derivative with respect to w. You can calculate, but I don't need it. Why I do not need it is because if I see what is del v by del t, this is actually equal to 0 and this is 1. So when I'm computing the determinant, this star derivative is going to get multiplied by 0. It doesn't matter. So this Jacobian is actually equal to W by P to the power half, right? So this is the transformation Jacobian. So what will we do now? What will we do now is that we will write down this density in U and V in terms of the transformed variables T and W, right? So that is what I'm going to do. So f of T and W. So this is the transformed one. So f of T and W is basically what? F of U and V. So in place of U, what do I write down? I write down T W by P to the power half. And in place of V, I write down W and I multiply this with the Jacobian. What is the Jacobian? Multiplied by W by P to the power half, right? That is what I will do. So this is the Jacobian. So this is what I'll do. So I substitute now. So I substitute, then after substitution, what do I get? I get a density and T in W. I get a joint density in T and W. So 1 upon root 2 pi e to the power minus U square, right? E to the power minus U square by 2. So U I'll substitute by this T. So e to the power minus half T square W by P, right? This is what I'll get. So this becomes little messy, but this is absolutely not difficult. Okay. So this is what you get by substituting this. And then the next part is 1 upon gamma P by 2 to the power P by 2, right? So this is what you had. Then you had e to the power minus V by 2. So V is only substituted by W. So you get this. Then you have V to the power P by 2 minus 1. So V is basically W. So P by 2 minus 1. And what do you get? You have to multiply it by Jacobian. So this is first density. This is second density. And you multiply it by the Jacobian. So W by P to the power half. Is this calculation clear to all of you? I have not done anything difficult. Just simple substitution, found out the Jacobian, and after Jacobian, I have come to this part. So the only genuinely interesting trick so far that I have done is that how I came up with the transformation. Okay, so this is the way I came up with the transformation. I have not told you how, but once you know that this is the transformation you want to make, all these calculations are not really going to be difficult. Okay, so now this is my joint density in T. Yes.
Wasn't it divided by the determinant of Jacobian?
No, it will be the way I have done. No, it will be done in this particular way. So it will be divided if you want to write down f of uv as f of tw and f of uv if you want to write in terms of tw, then the Jacobian will go to the other way. But right now, the way I have written it, I think it will be done in this way. Okay.
Okay, sir.
Yeah. So this is what you have. And once you have this, then what I want to find out, we want to compute the density of T, right? So we want to compute the density of this random variable T. So this T is basically this, right? U divide. Correct. So if there is a joint density in T and W, you want to compute density of T, what do? You find out marginal density of T by integrating W, right? So that's what I'm going to do. So this implies Ft is actually equal to integral 0 to infinity f of Tw dW, right? So I am just finding out the marginal density. That's all I'm doing. So this is basically equal to 1 by root 2 pi. So I'm taking all the constants out of the integration now. Then 1 upon gamma P by 2 into 2 to the power P by 2. Correct. So this is second constant that will come out. Then this P to the power half in the Jacobian you see 1 upon P to the power half, that will also come out. Then what am I left inside is integral 0 to infinity. You check e to the power minus half, I will take common. Then I have inside T square by P plus 1 into W. And what do I have? Then I have W to the power P P by 2 plus 1 by 2. So P plus 1 by 2 minus 1 dW. Do you all agree this is what I have? This is simple. This is just simple calculation that I have done. And now you realize this particular integral is basically a gamma integral, right? So you can use the formula of the gamma integral. So what do you get as your Ft is 1 upon root 2 pi 1 upon gamma p by 2, 2 to the power p by 2. 1 upon p to the power half. Okay, so this is what you will get. And now this is gamma integral. So in the gamma integral, what are the parameters? Alpha, lambda, right? So what is my alpha? So this is one parameter and this is another parameter, right? So these are the two parameters. That's why I did not disturb that -1. So if you see this, then using gamma density, do you agree that this is what I'll get? Gamma p plus 1 by 2, and then half to the power p plus 1 by 2 into t square by p plus 1 to the power p plus 1 by 2. Do you agree this is what I'll get? This is just gamma integral, gamma formula I have used. So this is something that you have already seen in Maths 1. Once again, we saw it when we were talking about densities. So this is what I'll get. And now you see there is this half to the power p plus 1 by 2 and you have 2 to the power p by 2. So you will have that only that half to the power half sitting over there, and you can adjust those things. And let me just write down. So there is a root 2 here, so that root 2 will also cancel with that 1 by 2 to the power half, right? Root 2 will cancel to root 2, then you are left with root pi. You have gamma p by 2, then you have this p to the power half, and you have this particular thing. Okay, so let me, after cancelling this half to the power p plus 1 by 2, what do we get? I'll just write this down. So ft, so you will get gamma p plus 1 by 2 divided by gamma p by 2. That is what you will get, into 1 upon root of p pi. That is what you will get, and 1 upon 1 plus t square by p to the power p plus 1 by 2. This is what you will get. And what is the range of t? The range of t is minus infinity less than this, less than. So this actually is the PDF. So this is the PDF of t distribution. Okay, PDF of u divided by square root of v by p, right? So PDF of this random variable, we call this follows a t density with p degrees of freedom. Okay, so what do we call? We call this follows t density with p degrees of freedom. Okay. So one thing that you can note here quickly is that when p is equal to 1, what happens? When p is equal to 1, what happens? Which density do we get? So p is equal to 1, gamma, in the numerator you have 1 plus 1, 2 by 2. So gamma 1 is 1. Then you have gamma half, which is root pi. And p is equal to 1, so root pi, you get 1 by pi. 1 by 1 plus t square, right? 1 by pi, 1 plus t square, you see Cauchy density, right? So this actually is Cauchy density when p is equal to 1. So there are few things that you should remember. So one of the thing is that this random variable does not have MGF, right? The reason why it does not have MGF is because for Cauchy density, moments do not exist, right? So if moments do not exist, then you cannot have moment generating function, because moment generating function is going to give you the moments. So in general, moments do not exist. So this does not have moment generating function. Second important property is that only p minus 1 moments exist. Only p minus 1 moments exist for TP. Okay, so if you have p degrees of freedom, then only p minus 1 moments exist. The third time is expectation of this random variable TP is 0 for p greater than 1, and you can find out the variance of this TP, which actually turns out to be p divided by p minus 2 for p strictly greater than 2. Okay, so these are certain things that you can remember about this T density, but the important thing is that how did you derive this T density? So you see the formulae really look difficult. Okay, formulae look really cumbersome, but if you think of it, if you know gamma density really well, if you know gamma density really well, then you have nothing to fear about, right? This is only gamma integral I am using repeatedly everywhere. And once you understand this, once the concepts are clear, I'm just doing this part, and I'm getting the answer, right? So this is my T density in general, and this is what is going to happen. Is that okay? So why we started with this T density? So the first of all, how does the T density look like? So you know T at P equal to 0 is Cauchy. So it also has a bell-shaped curve. So this is the typical PDF of T density with P degrees of freedom. Okay. So here also you have those like normal random variables. The tables are available. What is the difference between normal random variable and a T distribution? So they both have bell-shaped densities, but the tails in the T density are little thicker. That means that in the tail there is higher probability than that of a normal density. Okay, and as you increase the degrees of freedom to be close to something like 30 or 40, then the normal random variable and T distribution PDF are almost similar. But for the smaller values of P, you can see that the tail contains larger probability chunks than the normal. Okay, so this is what T density is. And similar to normal random variable, chi-square random variable also has these tables available with the degrees of freedom, and similarly T distribution also tables are available with degrees of freedom. So if you have TP, then you know you can always have these percent points that you can look up from the table. So in particular, if I take P is equal to n minus 1, why I am taking n minus 1? Because I am having x1, x2, xn random sample from normal mu sigma square, and now I know that x bar minus mu divided by s by root n follows T distribution with n minus 1 degrees of freedom, right? So it follows T distribution with n minus 1 degrees of freedom. So if I consider the PDF of this, then this is the percent point here. This is the percent point here, T n minus 1 alpha by 2 for an alpha chosen between 0 to 1. And what is the point? So the point on the x-axis is this, such that the area to the right of this point is alpha by 2. Again, because of symmetry of this particular random variable, we saw that mean is 0. So because of symmetry of this particular random variable, if you have this particular point, T n minus 1 alpha by 2 minus, then this area is also alpha by 2, and the area in between is actually 1 minus alpha. Okay, so this area is 1 minus alpha, and you can write down the probability statement now. So what is the probability statement that you can write down? The probability statement that you can write down is minus n minus 1 alpha by 2 less than x bar minus mu divided by s by root n less than T n minus 1 alpha by 2 is equal to 1 minus alpha. And if you simplify this, then what you will get is probability that x bar minus s by root n T n minus 1 alpha by 2 less than mu less than x bar plus s by root n T n minus 1 alpha by 2. This is actually equal to 1 minus alpha. So this is the confidence interval. So this particular guy here is the lower bound. This particular guy here is an upper bound. Both lower bound and upper bounds are calculable from data. Why? Because from data you will be able to compute x bar, you will be compute s. You know the size of the sample m, and you know that this percent point can be found out. So this particular real number T n minus 1 alpha by 2, this percent point can be found out from the normal tables, right? So once you have all these values, you can actually calculate L and U from data, and then you can say that you have, say, 90% confidence, 95% confidence based on what value of alpha you choose, that the true value of the parameter mu lies between these bounds. Okay, so not only you are giving a point estimate, which is x bar, you are actually giving an interval as the estimate. So you are saying that you have an interval, and in that interval you are saying that you have 90% confidence that the random variable, 90% confidence that the true value of the parameter will lie inside this interval. So this is something that is really very important. Okay, so in order to have such a analysis done, the interval estimation, we need to understand the density of x bar minus mu divided by s by root n. Okay, so that is what is really very important. So is this part clear? Is there any doubt?
Sir,
Yes.
sir, are there like TP tables to find this real number, right?
Yes. There are tables for chi-square t. Now I'll tell you about f distribution. So there are tables. Like you read the normal 0, 1 table, you can read chi-square table, you can read t table, you can read f table. So based on the degrees of freedom, there are tables available. From the table, you can find out these values, percent points. Okay, these points, these real numbers are called as percent points. Okay, so this is a percent point of this density.
Sir, so I mean, for how many P is it calculated? Like, is it like that only certain values of P come up again and again, or like every value of P is important?
No, so the table summarizes certain values of P, like it starts with 2, 3, 4, then maybe 100, 200 up to that. And certain values of alpha, typical values of alpha, they will have. And you can read the table like degrees of freedom versus percent point alpha values. And based on that, you can find out what is the P value in the table.
Okay.
As same goes for chi-square also. So there are tables available for these values. Okay. So once you are given these values, then you know how to calculate this L and U and so on. Is that okay?
Yes.
Okay.
Sir.
So, yes.
So sorry, sir. Sir, the doubt was like I had doubt like the estimate of mu is only as good as the estimate for S, right?
Estimate of mu is only
As good as the estimate for S, right?
Can you explain a little more, like what do you really want to mean?
Depending on how good the estimate of S is, the estimate of mu can have a variant, like it can vary, right?
Estimate of?
Sir, suppose estimate of S is some value alpha, sir, and then other case estimate of S is 1.2 alpha. The time like won't the like the range for like not let it be beta, sir, then won't the range for mu change?
So I'm telling you. So in this particular case, when sigma square was known, okay, when sigma square was known, the case one that we considered the random variable x bar minus mu divided by sigma by root n, which followed normal random variable. Do you remember that, Karthikeyan?
Yes, sir.
Yeah. So now the case we are considering is sigma square is unknown. So sigma square is unknown, then we will want to estimate sigma square also, as you have correctly pointed out. So that sigma square that we are trying to find out, guess from the data is guessed by S square. And as you have correctly understood that S square will also have certain variance sitting inside it. Is that the point you are making?
Yes, sir.
Yeah. So now because that S square is going to have that variance coming in. Now what do we want to do? We want to account for that variance in S square also when we are trying to say something about mu. That's what you are trying to say.
Yes, sir.
So that is now being accounted for by using a t distribution. So now this is also a random variable. This S also is a random variable. X bar is a random variable and S also is a random variable now. So no longer this will have a normal 0, 1. No longer it will have a standard normal random variable. No longer it will have a standard normal density. So the variation in S now needs to be accounted for. In other words, you want to find out the distribution of x bar minus mu divided by S by root n once again. And if you can find out the distribution of this particular ratio x bar minus mu divided by S by root n, then automatically whatever is the variation in S will be taken care of in the density of this random variable x bar minus mu divided by S by root n.
Yes, sir. Then in the final equation, why are we getting something dependent on S?
What are you getting?
Why are we getting something dependent on S? It should be something like a constant now. If you're taking care of the variance in S also.
No. So how will you actually compute these intervals? That is the question. So why S should go away? So the value of S, see the value of S will be important. Now in the previous example, if you remember, you had X bar minus sigma by root n, right? So that sigma is being replaced by S now here. That's all that has happened.
Oh,
so initially you are not letting go of sigma, right? Initially
yes,
you are not letting go of sigma, right? So initially if you see, did you let go of sigma? Here, sigma is still there, no?
yes, sir. But sigma is a constant because we already know it.
But X bar is not a constant, right? It's
Yeah.
variable. It's a random variable that is to be computed from the data.
Okay, fine.
So here also X bar is something that will compute from data. X bar is something that will compute from data. Now sigma is not known. It was constant previously because it was known. Now sigma is not known. So that also will compute from data. That's it. Does that make sense?
I understood now, sir. Thanks, I understood.
Okay, good. Very good.
That's why even after doing this, the curve is like Cauchy, right? We had a more sharper curve, like a better estimate when mu was like sigma was known. Like when sigma is unknown, it's becoming more random, right?
Not more random. It's a different distribution.
Like more diffuse distribution.
Yeah, the tails have higher probabilities now. Tails
Yes.
are thick. Yeah.
Yes, sir. Thank you, sir.
Anything else? Any other observation? Okay, so if this is understood, then it's already 8:55. So what I really want to do is, let me see if I can do it. This is a small piece of code I have written. Okay, so I just want to demonstrate it to show you that like what we are really doing. In a very simple case, I want to demonstrate it. And if it is done, then you will realize what is really happening. Okay, so I just want to see if I can do it. Okay, probably I can do it here. Okay. Okay, so let me what should I do now? Okay, I will stop sharing this. And I'll maybe share this. Okay. Just bear with me for a moment. Let me do this. Okay, so I believe the screen is visible to all of you, right? So yeah, so what I have done is following. Okay, so what I have done is following. So if you see this part of the code, what I have done is I have taken a random sample of size n from a normal density with mean 0 and variance 1, standard normal random variable. Okay, what I have done is this. I take this RANDN. So this is MATLAB I'm using to demonstrate. And what we are doing is that it has a sample of size n coming from normal random variable with mean 0 and variance 1. That's what I have done. And then I find out mean of this random sample, right? I find out mean of this random sample. So what I will do is I'll just take I is equal to 1 maybe. So I'm just drawing one random sample. And let me see if I can run this. Okay, so let us run this. So n is equal to 100. Okay, so if you see, I have taken n is equal to 100. That means I have a random sample of size 100. Okay, I have a random sample of size 100. And what I am doing, I am okay, so I am plotting two figures. So right now, okay, so figure unfortunately did not come out. Let me do it again. So if you see, when I am saying I am drawing a random sample of size n, what I really observe in real life. Okay, what I really observe in real life, let us first see. Okay, so let me. Okay, so let me print this X. Okay, so you see these data points. Okay, so you see different data points here. So like 0.6950, 0.4 minus 4310, this minus 0.1295. So these are different data points, and how many of these different data points are generated? 100. So this is something that is given to us, right? So this is the data, or this is the random sample that is given to us. So this is the realization of 100 independent and identically distributed normal 0, 1 random variables that we are seeing, right? And this I am plotting in a histogram here. So on the right panel, if you see the figure of histogram, what I have done is I have plotted the histogram here. And what is this histogram representing? Roughly, if you see, this histogram is of the shape, of normal density. Roughly, okay, I'm not saying it is exactly, but roughly. And what you can observe here, we have already seen from our probability theory that between -3 to 3, 99.99% of the probability mass is there. So all the 100 samples that are drawn, they all lie between the range -3 to +3. That was something that we had learned from theory, and that is something that we are seeing here directly. Is that okay? Up to this part, do you all follow what I'm saying?
Yes.
And I have just plotted those 100 realizations in a histogram, and the histogram looks very similar to a normal density roughly. So if I draw another random sample, okay, then obviously the 100 observations that I get this time will be different than the 100 that I got previously. Do you all agree? This is a different experiment.
Yes.
Oh my. Okay, so I pressed the wrong button, so it will take a long time to. So you will get a different set of realizations, right? So unfortunately, I pressed the wrong button. It will take a long time to get the answer. Okay, so this is the answer. Okay, so this is another thing. So let us wait. I think it is still running. Okay.
I guess it is not running.
It's not running. Okay, great. Then I think now it's running. So you see, now I have gotten a different sample. You see here, I have gotten a different sample. All the values are roughly between -3 to +3. This is a different sample, a different histogram, and this also looks very close to a normal density, right? So if you join the midpoints of the histogram, it will almost look like a normal density curve. Is that okay? Do you understand?
Yes, sir.
Okay, so now what I'm doing is that I'm going to draw. So I is equal to 1, I draw one sample. What I'm going to do, I'm going to draw 100 samples. Okay, what I'm going to do, I'm going to draw 100 samples of size n. And what am I doing? I'm going to find out mean of this sample. I'm going to find out mean of this sample, and I'm going to store that mean in this, right? So I will have 100 means for 100 samples. So here you check what is the value of the mean. So the mean value is x, which is equal to minus 0.0144. Okay, so pretty close to 0, right? So this is the sample mean that I have calculated. So this is my estimate for the mean. So based on the data that is given, so from the evidence that I see, my point estimate is this, the blue number which I have highlighted, minus 0.0144. That is the estimate for the mean mu. So original mean, true value of the parameter is 0. I know that, but now I'm pretending I don't know. And this is what I have. So this is the value I get. If I draw a different sample, then I'll get a different value of mean. Okay, so this is what is going to happen. Every time I draw a sample, I get different value of mean. So what I'm going to do, I will have different 100 values of means for each of the 100 different samples. And I want to understand what is the what is the PDF of mean mu. Okay, so we know in theory if sigma square is known, it looks like it is a normal density. If it is not known, then that x bar minus mu divided by s by root n will be T density. So in either case, you should have bell-shaped curve. So let us see if we get bell-shaped curve for M also. So this code, let it run, and let us see. So now M is, so this figure 2, what you are seeing here, this is one random sample. Okay, so this is one random sample, the last one, and you see this is the distribution of mean, roughly again a bell-shaped curve. But what you have to observe here is the following: the range, the spread of this. It is between minus 0.2 to 0.2, whereas this range is going to be from minus 3 to plus 3. Do you understand? The sample will go from minus 3 to plus 3, but the mean, the variation in mean is much less. And why is that? Because you know that the variance is sigma square by n. Here n is 100. So sigma square by n. So sigma by root n. So sigma is 1, root n is 10. So 1 by 10. So 3 by 10 to minus 3 by 10 to plus 3 by 10. So minus 0.3 to 0.3 is the acceptable range. 99.99% of the probability mass is between minus 3 by 10 to plus 3 by 10. Do you all agree how I got the number minus 3 by 10 to plus 3 by 10?
Yes,
sir.
Yeah, so you see here the spread is much less, between minus 0.2 to 0.2, right? So theoretically between minus 0.3 to plus 0.3. Whereas if you consider the sample, if you see the PDF of the random variable, then you see the spread is between minus 3 to plus 3. So this is what you see. This is what you see from this particular illustration. So you see how the data is really coming out and how this mean is really going to play a role. Okay, so this is what you had. So let me comment this out maybe, and let us see what we can say about the okay, so this is what I'm going to do. So again, what I am really doing here is I will take a sample of size 100 again, let us say for example. And what I am doing is I am generating a random sample. But now what I'm doing, I'm generating a random sample of size n. It's a normal random sample. It's a normal random sample with mean 3 and variance 1. Okay, the mean is 3 and variance 1. And what I am really doing here is I am calculating the lower and upper bounds of the confidence interval. So M is the X bar that I will calculate from the data. This percent point 1.65 is actually computed Z alpha by 2. So this Z alpha by 2 is such that the probability to the right of this point, so 1.65, the probability greater than or equal to 1.65 is I think 0.05. Okay, so this percent point is when alpha is equal to 0.1. Okay, I'm trying to find out 0.9 probability or 90% confidence interval. So this is Z alpha by 2 and this is Z alpha by 2. I have assumed that I know the variance. So I'm taking sigma divided by square root of n, right? So n is the sample size, so I'm taking divided by square root of n. So this is my lower bound, this is my upper bound. So what am I going to get? For I is equal to 1. So for one sample, let us say for example, I am going to get a confidence interval L and U. Okay, so let me run this and see what I get. So the sample that I am going to have here. So the sample, don't worry about the figures I will show later. So the sample that I have here of size 100 is this sample, right? So these are the 100 points that I have generated. The mean is 3. So you can see here, these are the values of the sample. Okay, so this is the sample that I have generated. The mean is 3. So this is the sample of size 100. Okay, so what is the mean of this sample? The mean of this sample M is actually 2.938. Okay, so the actual value of the parameter mu was 3. We don't know that. We are pretending now that we don't know. In reality here we are simulating, so we know what is the value of mu. But in real life we will not know this value of mu. And what is L and mu here? You see L, lower bound is 2.77. M, the upper bound is 2.93. Okay, so sorry, L and U. And U, the upper bound is this. So if you see M, L and U, if I print it like this, then you see the true, then the point estimate is this. This is the point estimate of the parameter, and this LU, lower bound and upper bound, this is the interval that you are calculating. This is the interval that you are calculating from the data, and you are saying that you are 90% confident that the true value of the parameter lies inside this interval. Okay, so in this particular instance, the value of the true parameter, which is 3, we know that actually lies inside this interval. And roughly you see what is the length of the interval. Roughly the length of the interval is 0.35 or something. Right, so that is the length of the interval. So this is what we have seen, right? So what I'm going to do, is I'm going to repeat this exercise, point estimate, lower bound and upper bound for the confidence interval. I'm going to repeat this experiment 100 times. Okay, so I'm going to draw 100 samples and 100 times I'm going to repeat this experiment, and I'm going to see what happens to this lower bound and upper bound values. Okay, so I'm going to see what really happens. So let me see this. Let me run this and see what is happening. So now you see what I have done. What I have done is this red line that you see here, the red line that you see here. So for 0 to 100. So what I have really done is that this red point corresponding to 1, 2, 3, 4, 5, 6, they are the lower bounds and they are the upper bounds for sample number. So suppose for sample number 20, the lower bound is coming out to be 2.99244 and the upper bound is coming out to be 3.34105 for sample number 20. And what is the size of the sample? Size of the sample is 100 in each case. So this is the confidence interval that I'm getting for sample number 20. And you can see what is the mean by printing out the 20th number in the array, right? So there are certain places. So for example, this place, okay, whatever is the sample number. So if you see this sample number 55, the lower bound actually happens to be 3.1 and the upper bound for this sample number 55 happens to be 3.4. So here for the sample number 55 that we drew, the sample number 55, what happened? The true value of the parameter does not lie inside the interval. But then we said that we are only 90% confident, right? So if you drew 100 samples, then roughly what you're saying, out of the 100 samples, there is a possibility that there will be 10 samples where the true value of the parameter will not lie inside this interval. Do you understand what I'm saying?
Yes, sir.
Yeah, so that is what we really are doing. So here I am trying to show you that this typically this red line and blue line should always have this true value of the parameter which is equal to 3. So I should have drawn a straight line here. So that always lies, the line always lies between this blue curve and red curve. But there is a breach, and what is the breach? Probability of having that breach is 0.1, because we are only saying that we are 90% confidence, and that 90, where is it coming from? From the percent point that I have chosen here. Okay, so this is Z alpha by 2, where alpha is equal to 0.1. Okay, so with that value, I am saying that this is what is really going to happen. Is that okay?
Yes, sir.
Okay, so if you draw once again, you see, because this is probabilistically this is going to happen. I will draw another 100 samples. I do not expect to see the same curves again. Now you see the curves are different, right? Now the curves are different and see here at this particular instance, sample number 4, the lower bound is 3.01. That means that the mean is outside the interval, right? So you can see how many number of intervals are there. So here the upper bound you see is less than 3, roughly, I think, if I'm correct. So in this particular case, yeah, the upper bound is less than 3. It is actually 2.94 for sample number 66. So the interval does not contain the true value of the parameter 3. But in almost all other cases, you see that the interval is going to contain the true value of the parameter, right? Wherever there is a breach, the roughly 10%, right? So this length, the vertical length you see here is actually the length of the interval for each sample. That length depends on many things. One of the things that it depends on is the sample, right? So if I have, instead of 100 samples, 1000 samples, you see the y-axis range. Okay, here it is between 2.8 to 3.2 roughly. Now if I increase the number of samples to 1000, what do you expect to see? The length of interval is going to go down. Why? Because you are dividing by square root of n. So instead of 10, now you are dividing by square root of 1000, right? So you see the range, the length has reduced drastically from 2.95 to 3.5 roughly, right? So that is what has happened. And at the same time, you still have 90% problem, right? So you see here, there are several peaks here, 4 I can see directly. And 5, 6, 7 maybe. So there are 7 intervals possibly which do not contain the true value of the parameter 3. But that's fine, right? We were allowed to have like 10% breach. But the length of the interval, the length of the confidence interval is smaller. So this is something that happens with increase in number of samples. Is this clear? And the same analysis I can do for sigma square. The same analysis I can do for t random variable when I'll assume that this is not known. So when I assume that I don't know sigma square, this one now will get replaced by s square, the estimate of standard deviation, right? S. So I'll find out s square sample variance. I'll take square root of the sample variance, and instead of this one, I'll substitute that sample variance, right? And this 1.65 will no longer be 1.65. I'll look up the t table and I'll find out the percent point from the t table. These are the two things that I will change. And once I change these 2 points, then I will have different values of lower bound and upper bound. And once I have different values of lower bound and upper bound, then I will see different lines here. Is that okay? Now, do you understand what we really have done? And when you work with real data, this is what is really going to happen. Is that okay? So when you work with real data, you will never know this value 3. You will never know that the mean is 3. So if you see 2.93 as your point estimate, you have to take that as your point estimate only. Or you have to take this as your interval estimate. There is no other way. In real life, you do not know this value. So from the data, you will conclude that this is the value. How good that value is, for that we are trying to understand these distributions. We are trying to understand how the increase in number of samples helps in analyzing the variation in the point estimate and so on and so forth. Is that okay? Do you roughly get the idea of what we really are doing and why we are doing it?
Yes, sir.
Any other thing that you want to say here?
Sir, can you share this code with us?
Yeah, I can share this code with you, no problem, but it's in MATLAB. So if you're using R or Python, then I think you have to do it differently, but I will share this code, no problem. If you really want to,
Sir, from institute.
yeah, so that's what I'm saying. You have MATLAB license from institute. If you don't have, that's why I was trying to demonstrate this. I am actually using online MATLAB. Using my institute mail ID, I am actually using online MATLAB. So if you do online MATLAB in Google, you go to this website, try to register using your institute ID, and then you will get this MATLAB access. So I'm using that MATLAB access. I don't have MATLAB installed on my laptop, but I am using it online. That's why it takes a little longer to execute the code. But if you have MATLAB in your laptops, then your institute has provided license. I will share this code with you, no problem. But as you can see, the code is really very badly written. Okay, I'll try to kind of sanitize this and then send it to you. But I'll share. If you want, I can definitely share this code with you. Is that okay? Is that okay?
Sir.
Okay, excellent. So let us again go back to this theoretical development, and let us again try to see one more distribution, which is F distribution. Okay. Okay. I will just take a quick 1 minute break. I'll drink water and then we can continue. Okay, just 1 minute. let us continue our discussion. So I hope now that these things are clear, I will just go further, and now I'll kind of work with two distributions. Okay, so comparing okay, so far we only had one density. We had only one population, so to speak. Okay, so this is another terminology that people use. So in the previous discussion that we had so far, what we had done was we had only a random sample from one density, normal mu sigma square, right? So now what I'm going to do really is I'm going to draw a random sample from two densities, and then I want to compare the variances of these two densities. Okay, so the problem that I am going to have is that x1, x2, xn is a random sample from normal mu1 sigma 1 square. Okay, so x1, x2, xn is a random sample drawn from this normal mu1 sigma 1 square. Is a random sample drawn independently. Okay, so I'm doing independently from the random sample y1, y2 up to ym from another normal density mu2 sigma 2 square. Okay, so there are two densities and I want to compare sigma 1 square and sigma 2 square, right? So I want to compare sigma 1 square and sigma 2 square. Compare meaning I want to find out like which distribution has higher variance. That's what I want to find out. So obviously what I will look at is ratio s1 square by s2 square, right? I look at this ratio of s1 square by s2 square, and then from this ratio I will decide like I will like to decide what is really happening, right? So similar to this s1 square by s2 square, I will have to set up a distribution, right? So the statistic or the test statistic that I'm going to use is s1 square by sigma 1 square divided by s2 square by sigma 2 square. Okay, so this is what I am really going to look at. So this is the random variable that I'm going to look at, and I will show that this random variable follows f density with m minus 1 degrees of freedom. Okay, so it follows this particular f density, and once you have this, then computing s1 square by s2 square, and we can have all those things in place. Okay, so this is what I really want to do. So one thing that you have to see here is that s1 square by sigma 1 square. So if I had m minus 1 s1 square by sigma 1 square into, so this random variable, okay, consider this random variable s1 square by sigma 1 square. So this is actually n minus 1 s1 square by sigma 1 square into 1 upon n minus 1 divided by m minus 1 s2 square divided by sigma 2 square into 1 upon m minus 1. This is what we have. So this is actually equal to u divided by n minus 1 divided by v divided by n minus 1. And what is u and v? Where u follows chi-square random variable with n minus 1 degrees of freedom, and v follows chi-square random variable with m minus 1 degrees of freedom, right? So, and further, u and v are independent. Is that okay? So what is it that we are looking at? We are looking at ratio of two chi-square random variables, not only the ratio of chi-square random variables, chi-square random variable divided by its degrees of freedom divided by chi-square random variable divided by its degrees of freedom. That is what we are really looking at, and we are interested in finding out density of this u and v are independent. So in general, what do we want to do? In general, let u follow chi-square p and let v follow chi-square q. Okay, so in general, what we are trying to do, we are trying to find out density of this. So let u follow chi-square p and v follow chi-square q, and u and v are independent. So why I'm saying u and v are independent? Is it something that I'm just saying here? No, u and v are independent. Why the independence is coming? The independence is coming because the two samples are drawn independently of each other, right? So first sample from the population is independently drawn from the second sample by one by two. There is no statistical dependence in this. So that's why u and v are independent, right? So that is something that we have to assume. So u and v are independent, right? So then compute the density of this random variable. Compute the density of random variable u by p divided by v by q. That is the density that you want to compute, right? This is the density that you want to compute. So what are we going to do? We are going to do the exact same thing that we did for T density. What did we do for T density? We considered u and v. We took the joint density of u and v. We did some transformation, and after doing the transformation, we integrated out one part so that the remaining marginal density that we had, that was the density that we were trying to find out. Exact same logic we are going to apply here. Okay, so we want to compute this density, compute the density of this. So this density is called as F density. F density with p minus 1, p comma q degrees of freedom. Okay, so with p comma q degrees of freedom. So degrees of freedom is only like parameters, okay? And you already know in chi-square degrees of freedom basically relate to the alpha lambda, right? So those parameters. So I will now write down the joint density of u and v directly. So the joint density, you just check and tell me if it is correct. Joint density of u and v is basically FUV is equal to 1 upon gamma p by 2 to the power p by 2, okay, into e to the power minus u by 2 u to the power p by 2 minus 1. And the same thing I'll have to write for v. So gamma q by 2 to the power q by 2, correct? Then e to the power minus v by 2 v to the power q by 2 minus 1. What is the range of u and v? 0 less than u less than infinity and 0 less than v less than infinity. Why is this range? This is the range because u and v both are chi-square random variables. They are non-negative, right? So this is the density, joint density of uv. Why I have taken product? Because u and v, since u and v are independent. Since u and v are independent, what happens? The joint is actually product of marginals. That's what I have done, right? So I do this substitution. So what is the substitution I do? So the substitution that I do is x is equal to u by p v by q. Okay, so this substitution is what we really want. So the density of this particular random variable is what we want, and I define another random variable v to be equal to v by q. Okay, so this is what I get. So clearly you see range of x and range of y is also between 0 to infinity, right? So that's clear from here. And what do we get? You can see u is equal to actually x. So u is equal to p into x into v by q. So that v by q actually is y. So u is actually equal to pxy. And similarly, what is v? V is actually equal to, and v is actually equal to qy. So u is pxy and v is equal to qy. So the Jacobian of the transformation, the determinant, so del u by del x, del u by del y, del v by del x, and del v by del y, right? So this is the Jacobian. So this will be equal to, if you see the calculation, what will this be? Py px 0 q, which is equal to p q y. Is that right? That is the Jacobian, PQY. Is that okay?
Yes,
This
sir.
calculation. Okay. So now once I have this, then I will write this down. So f of xy is basically f of uv. So what is u? U is pxy. F of pxy qy into the Jacobian. So the Jacobian is pqy. Is that right? So this is what I'll have. So wherever I see u, I'll replace u by pxy. Wherever I see v, I'll replace v by qy multiplied by Jacobian. So I want the density of x. So this will be actually equal to, I will integrate out y. So the marginal, that's what I'll find out. So this I'll just write it down now. Gamma p by 2 to the power p by 2. So once again, you will see that this is nothing. Only the expressions are cumbersome. Once you are through it, there is no difficulty, right? So I am writing some terms together. Q by 2 to the power q by 2. Correct. Then I have e to the power minus pxy by 2 into e to the power minus qy by 2. Correct. So that is what I have. Then I have pxy to the power p by 2 minus 1. I have qy to the power q by 2 minus 1. And then I have pqy, which is nothing but Jacobian, and I'll multiply by dy, right? That's the integration that I'm looking at. So I don't have enough space, but I hope you understand this whole thing is actually the integrand. And how I have written it down? I have written it down f pxy qy into Jacobian, and I have integrated y out. So if you understand this, then I'll take the constants out. So the constants are coming out: gamma p by 2, gamma q by 2, then 2 to the power p plus q by 2. That is what you have, right? And then you have this px. So px to the power p by 2 minus 1 will come out. It's independent of integration. Then this q to the power q by 2 minus 1 will also come out. And this pq will also come out. Is that okay? So these are all the things which integration is not going to affect. They are all constant. And inside the integral, what do you get? Inside the integral, you get multiplied by e to the power minus half px plus q y, and y to the power p plus q by 2 minus 1 dy. Is that okay? And again, you observe that this is actually nothing but the gamma density. And what will it evaluate to? This gamma density, what does it evaluate to? It evaluates to gamma p plus q by 2. And this particular factor raised to the power p plus q by 2, right? That's what this gamma density evaluates to. So let us write that down. So I will write this down as fx is equal to gamma p plus q by 2, that is coming out from that gamma, divided by gamma p by 2, gamma q by 2. Okay. Then I have 1 upon 2 to the power p plus q by 2, right? So this is what I had. So this factor 1 upon 2 to the power. Then I have p to the power p by 2, q to the power q by 2 into x to the power p by 2 minus 1, right? So this is the simplification. This is the simplification of this term, right? So maybe if you want, I will just mark it like this. So this part, sorry, this part is coming here like this. Then this part is coming here like this. So this part is coming here as this part. Then this part, this particular simplification is coming here. So this is the simplification that you see. And then whatever remains is actually the integral, right? So this gamma p plus q by 2 is actually the integral. So this multiplied by this multiplied by this. So I'll write in the next line 1 upon px plus q to the power p plus q by 2 into 1 by 2. So this divided by 2 to the power p plus q by 2, because there is a half there. So that is what is going to happen. So this is the factor that I will get, right? So this is what I'll get. And now you see Now you see I can kind of cancel this 2 to the power to this particular thing, and if I take q common, if I take q common from this denominator, then what will happen? You will have gamma p plus q by 2 gamma p by 2 into gamma q by 2. So this is the factor that you'll have. Then you will have you just see if you agree with this calculation, then you'll have p by q to the power p by 2. Then you will have x to the power p by 2 minus 1 divided by 1 plus q by 1 plus p by q, because I'm taking q out. 1 plus p by q x to the power p plus q by 2. Okay, so this is the density fx. What is the range of x? 0 less than x less than infinity is equal to 0 otherwise. So this is actually the PDF. This is actually the PDF of f density. Okay. So this is the PDF of f density. Again, it looks little cumbersome, but if you really see, it is not that difficult. Okay, it is not that difficult. And what do we say? We say that x follows f density with degrees of freedom p and q. Okay, so p and q degrees of freedom, basically they are parameters, and once you know p and q, you know the entire density. So basically these are the parameters that you are really looking at. Okay, and once you have this, then f distribution also with degrees of freedom, so it has some shape like this. It is a positively, so its support is positive, and suppose this is the PDF of f n minus 1 m minus 1. Okay, so why I'm taking this? So then what I will be able to do? What I will be able to do is really I'll be start with this x1, x2, xn. So let me write it down anyway. x1, x2, xn are IID normal mu1 sigma 1 square, and y1, y2 up to ym are IID normal mu2 sigma 2 square, and these are also independent, right? All the xi's are independent of all the yi's. That's what we really mean. Okay, so that is what we have. And then you can have the percent point here again. So this percent point here, f n minus 1 m minus 1 alpha by 2. That means that to the right you have probability alpha by 2. Similarly, this point, because of non-symmetry, f n minus 1 m minus 1 1 minus alpha by 2. That means that to the right the probability is 1 minus alpha by 2. That means that to the left the probability is alpha by 2, and in between you have this probability which is equal to 1 minus alpha. 1 minus alpha. And what is the probability statement you can write down? The probability statement that you can write down is f of n minus 1 m minus 1 1 minus alpha by 2 is less than or equal to s1 square by sigma 1 square divided by s2 square by sigma 2 square is less than or equal to f n minus 1 m minus 1 alpha by 2. This probability is actually equal to 1 minus alpha. And then you can find out where is the value of the ratio sigma 1 square by sigma 2 square lying by looking at this particular thing, right? So looking at this ratio, you can find out left hand limit less than or equal to sigma 1 square by sigma 2 square less than or equal to right hand limit, and that will be your lower bound and upper bound. Is that okay? Is that okay? Do you understand this f distribution? Huh? Priyanshu, is it okay? Yes, Vishwan. Vishwan, go ahead. Okay, Priyanshu, you can ask.
So in the previous slide,
Yes, sir, can't we?
हाँ बोलो Vishwan, please ask. I think Vishwan has internet issues. Let's wait Priyanshu. Vishwan, please ask question.
Yes, sir, can't we derive that f distribution from the distribution of quotients, distribution of quotients of two gamma distribution?
That is what we have done, no?
Sir,
What is the
for two gamma densities, right? then a simple
chi-square is a particular case of gamma density, no? Chi-square is a particular case of gamma density. Why I need chi-square? I need chi-square because I am interested in doing this. See, you can take ratio of two gamma densities. That's not a problem. You can derive the ratio of gamma densities. What is the distribution? You can do that very well. But I am also doing exactly the same thing, but I am slightly modifying it. So I am dividing it by P and Q, the gamma random variables, because my thing comes in that form, right? S1 square by sigma 1 square, S2 square by sigma 2 square. That's the form that I get. So that's why I'm doing it this way. Is that okay? But chi-square is a gamma density anyway, with special choice of parameters, right? So that's what we have.
Yes, sir.
Yeah. Okay, Priyanshu, do you have anything to say?
Yes.
Yeah.
Sir, where did this PQ go? I mean, there was P to the power P by 2 minus 1 and Q to the power Q by 2 minus 1. So,
So here that P to the power P by 2 minus 1, Q to the power Q by 2 minus 1 into PQ. I added that P. So P is 1, right?
I missed in the expression. Okay, sir. Yes, sir.
So that PQ is coming from Jacobian. So that's why I'm getting P to the power P by 2, Q to the power Q by 2. And then here I'm taking in this PQ plus PX plus Q, I'm taking Q out, which is common. So 1 plus P by Q x to the power this, and then I'll have Q to the power 1 by Q to the power that P plus Q by 2. So that gets adjusted in this expression. P plus Q, P by Q to the power P by 2. Is that okay?
Okay, sir. And so that is beta PQ also. I mean, it is coming very nice.
Yeah, if you want to write, yeah, you can write down it in terms of beta PQ. That's correct. Is this okay? So this is how you actually derive. So if you think of it, this is not really very difficult, the derivations. Important thing is to understand this substitution trick. So what substitution we have done for T and F, you can remember. In general, it may not be easy to guess, but the practice will help you. In problems that you are trying to solve, you please remember this. Okay, so this is why I derived this, because I can show you how the transformation really works of two variables to two variables. One to one variable we had actually done in detail in the class. So UV transforming to XY we had not done in the class. I just had given you the formula. So now I am actually demonstrating it, how it really works. So if you see problems similar to this, this is what basically you are required to do. Is that okay? Are you all okay with what we have done so far? Okay, so one thing that you can observe here, in F is the following. Okay, so suppose I have a T random variable. T random variable. Okay, so the T random variable, basically, suppose I say I have a random variable U, which is normal 0, 1. I have a random variable V, which is chi-square P. Okay, and I have U and V independent. Correct? I have U and V independent. Then U divided by square root of V by P, we know follows T density with P degrees of freedom. We already proved it. What we just now proved is U square divided by V square, U square divided by V by P. Okay, U square divided by V by P. So what is the density of U square divided by V by P? So if U is normal 0, 1, what is U square? It is chi-square 1. Is that right? And this is basically U square divided by 1 divided by V by P. So you have a chi-square density divided by degrees of freedom. Then V is also chi-square density divided by degrees of freedom. What will this follow? This will follow F1P. Is that right?
Yes, sir.
Yes,
It will follow F1P. So roughly what you can remember is square of a t random variable is f. So t, I will write tp is f1p. Okay. This is something that you have to observe. So what I will do now is I'll quickly summarize all these things that we have kind of learned about. Okay, so what we have done is that we have looked at these random sample from mu sigma square, normal mu sigma square. Okay, so all these analysis that we had done, we had derived these densities, sampling distributions and all. They work very well for normal, but if you change normal to some other distribution, then it is difficult. Why is it difficult? Because the normality assumption was key. Only because you had normality assumption, you can speak of chi-square. Only because you had chi-square, you can speak of t, and then you can speak of f. Right. So normality assumption is really very important. As soon as you let go of normality, then all these analysis need to be done separately. So the x bar and sigma square estimators will be still okay. X bar and x square, those estimators are still okay, but their distributions and their statistical properties, for that you need to derive them separately, and it's not easy task always. Okay, in case of normal density it was easy, so I kind of demonstrated, but in general this thing is not really very difficult. This is one comment that you have to remember. Okay, the second thing that I want to just like summarize here, I just want to summarize here is the following. So you have x1, x2 up to xn, a random sample from normal mu sigma square. Okay, normal mu sigma square. Then what do we know? We know mu unknown, sigma known. What do we know? X minus x bar minus mu divided by sigma square by n. Sorry, x. So what I will just say is that x bar follows normal density with mu and sigma square by n. Okay, and x bar minus mu divided by sigma by root n follows normal 0, 1. So you have the standard normal random variable, right? Then the second thing that we know is that sigma square, so s square is an unbiased estimator of sigma square. Okay, it's an unbiased estimator of sigma square. And what do we know? We know that n minus 1 s square by sigma square follows chi-square with n minus 1 degrees of freedom. The third thing that we know is that x bar minus mu divided by s by root n actually follows t distribution with n minus 1 degrees of freedom, right? These are the things that we know. And if x1, x2 up to xn follow IID normal mu sigma square, mu1 sigma 1 square, and y1, y2 up to ym follow IID normal mu2 sigma 2 square, and they are all independent of each other, right? Mutually independent. Xi's and yi's are independent of each other. Then what do we know? We know that s1 square by sigma 1 square divided by s2 square by sigma 2 square follows f distribution with n minus 1, m minus 1 degrees of freedom, right? So this is what we proved. So in general, what do we know? In general, what do we know? So this is something that you have to remember. Okay, this is very important. In general, let Z1, Z2 up to Zp be IID normal 0, 1, standard normal random variables. Okay, standard normal random variables. Then Z1 square plus Z2 square plus Zp square. What is the distribution of this? This follows chi-square density with p degrees of freedom. What is chi-square p? Chi-square p is actually gamma p by 2 half. Correct? Chi-square p is basically gamma p by 2 half. So this is the density. This we had already seen. Yes, Vishwan?
Yes, sir.
Okay, so this chi-square p is gamma p by 2 half. So what you have to remember? Sum of squares standard normal random variables. follow chi-square p. Okay, so this is something that you have to remember. Sum of squares of standard normal, right? What is the second thing that we saw? The second thing that we saw is that suppose u follows normal 0, 1 and v follows t with, v follows chi-square with p degrees of freedom and u and v are independent. U and v are independent. If that is the case, then what happens? Then we saw that u divided by square root of v by p actually follows t distribution with p degrees of freedom. Is that okay? So today we saw this. And what is the third thing that we saw today? The third thing that we saw today is suppose u follows chi-square p, v follows chi-square q, u and v are independent. U and v are independent. Then what did we see? We see that u by p, v by q. This ratio follows f density. So this ratio follows f density with p comma q degrees of freedom. Okay, so this is what we have done. So these things you have to remember. Okay, and in this case of normal also, one thing that you have to remember always. Okay, so I forgot to write down that suppose x follows normal. So how do we normalize? X follows normal mu sigma square implies that x minus mu divided by sigma follows normal 0, 1 always. Okay, so this is what we have. X follows normal mu sigma square. Then how do you normalize it? X minus mu divided by sigma. That is how you normalize it. So this is what you do, and this sum of squares of these things will be gamma and these results. Okay, so these are the important results. These results are really very useful. Okay, I just have uploaded this assignment 8. Okay, I have uploaded this assignment 8 just today morning. Please have a look at that assignment 8. Try to solve the problems from the assignment 8. So I am intending to maybe if I can just couple of problems I'll try to solve now. I have 5-10 minutes. So let me solve a couple of problems. Okay, so you will get the idea of what this is. Assignment 8. Problem 5, let us say. Okay, so I have chosen 2 problems, so I'll quickly show based on these things how do you do calculations. Okay, so once you understand how do you do calculations, then similar problems you can attempt in the exam. So that's what I'm doing. So the problem you might not have seen, I'll just write down x1, x2, xn and xn plus 1 are IID normal mu sigma square. Okay, so they are all independent identically done. X bar and S square. So S bar and S square are sample mean and sample variance respectively. Sample mean and sample variance. Sample variance. And important thing is that they are based on these observations x1 up to xn. Okay, so they are sample mean and sample variance of x1 up to xn. So X bar basically summation xi I from 1 to n divided by n, and S square is 1 upon n minus 1 summation I from 1 to n xi minus x bar whole square. Okay, so this is what x bar and S square are. Okay, and now the question is find the distribution. Find the distribution of root of n by n plus 1 xn plus 1 minus x bar divided by s. Okay, so this is the distribution we want to find. So I mean this requires a little bit of practice, but now when I'm looking at this root of n by n plus 1 xn plus 1 minus x bar divided by s. So xn plus 1 minus x bar divided by s. Okay, so now you see xn plus 1 is anyway independent of all x1, x2, xn. So xn plus 1 is independent of x bar, xn plus 1 is independent of s. That is the observation first you will make, right? So this is the observation. Xn plus 1 is independent of x bar and s, right? Because x bar and s square are dependent only on x1 up to xn, and we have given IIDs, so this is done. Okay, so now first thing that you see is x bar. What is the density of x bar? X bar follows normal with mean mu and variance sigma square by n. Do you all agree? Xn plus 1 follows normal with mean mu and variance sigma square. So can you tell me what is the density of xn plus 1 minus x bar? Xn plus 1 minus x bar. What will be the mean? Mean will be 0.
Mu 0, 0.
0 and variance will be sigma square by n plus sigma square, right? So mean will be 0 and variance will be sigma square by n plus sigma square. That means that xn plus 1 minus x bar will follow normal with mean mu and sigma square into 1 by n plus 1. So n plus 1 by n, is that right? That is the density of xn plus 1 minus x bar. Is that okay?
Yes.
So this will mean that xn plus 1 minus x bar divided by sigma root n plus 1 by n will follow normal 0, 1. Is that okay?
Yes.
Yes, sir.
Now note that xn plus 1 minus x bar is independent of s square. Correct. So this is something that that is there. X bar is independent of s square. Xn plus 1 is independent of x square. So xn plus 1 minus x bar is independent of x square, right? So because of this, I can do this. So independence between xn plus 1 and x bar was used here to find out what is the variance, right? So there is no covariance term. I just added variances because of independence of xn plus 1 and x bar. Now, because of this, what I can say, the same trick that I did some time back, I will replace this sigma by s. So what will be the density of this? So you're looking at the ratio of standard normal divided by this, right? So this, how will you handle? So this is not really very difficult. It is xn plus 1 minus x bar divided by sigma, and this square root of s square by sigma square into n by n plus 1 square root, right? So this is like ratio of normal 0, 1 divided by square root of chi square degrees of freedom, right? So this, do you all agree, will follow T density with how many degrees of freedom? N minus 1. Because s square,
Yes.
n minus 1 s square by sigma square follows chi square with n minus 1 degrees of freedom. Correct? This is something that we have already seen. So this particular random variable that you see here, what is it? It is actually the ratio of normal 0, 1 divided by square root of chi square of n minus 1 by n minus 1. Is that right? And you know that this normal and chi square are independent, so it has to be a T distribution. This observation, second observation that we have seen. Is that okay? So this is how you will kind of tackle these type of problems. Okay, so let me see if I can another problem. Okay, so let me see. So let x1, x2, xn be random sample. From normal mu sigma square. Okay, so this is a random sample from normal mu sigma square. 1 is less than k less than n. Okay, so this is given for k, which is between 1 and n. We define u to be equal to 1 upon k summation xi I from 1 to k. We define random variable v to be equal to 1 upon n minus k summation I from k plus 1 to n xi. So what I have done, I have divided the given random sample x1, x2, xn into two parts, x1, x2 up to xk and xk plus 1 up to xn, right? So that is what I have done. And I am calculating this s square. I am taking 1 upon k minus 1 summation I from 1 to k xi minus u square, and t square is 1 upon n minus k minus 1 summation I from k plus 1 to n xi minus v whole square. Do you understand what I have done here? What are these u, v, S square, T square. Do you understand what we have done? So we have split the given random sample x1 up to xk, that is one group I have, and xk plus 1 up to xn, this is second group I have. So these are the two, this is the given random sample divided into two parts. So there are k independent random variables here, n minus k independent random variables here, correct? And this group of random variables is also independent of this second group of random variables, right? So all these independences are already there. So if that is the case, then what can we say? What can we say? What is the distribution of U? Can you tell what is the distribution of U? U follows normal mu, and what is the variance of U? Can you tell?
Sigma square by
K.
Correct. What is the density of V? Normal. What is
mu
the mean?
mu comma sigma square by
Mu
n minus.
divided by n minus k. What is the density of S square? What is the density of S square? So not really S square. What should I really ask is k minus 1 S square by sigma square follows chi square with k minus 1 degrees of freedom. And similarly, n minus k minus 1 T square by sigma square follow chi square with n minus k minus 1 degrees of freedom. Is that okay?
Yes, sir.
Do you agree with this? Now, if that is the case, then density of U plus V by 2. Can you tell what is the density of U plus V by 2? You know the density of U, you know the density of V. You know that U and V are independent. U and V are independent, correct? So this is what we know. U follows normal mu sigma square by K. V follows normal mu and sigma square by n minus k. So what is the density of U plus V by 2 from here? Can you tell? What will happen? What will happen to the means? Mean will be mu. What will be the variance?
1 by 4 times sigma square by k plus sigma square by n minus k.
Correct. 1 by 4 times sigma square by k plus sigma square by n minus k. Is that okay? This is the density of U plus V by 2. So now the second question I want to, the second question is asked is density of this W2 is equal to k minus 1 S square plus n minus k minus 1 T square divided by sigma square. Okay. So if you see this, what this really is k minus 1 S square by sigma square plus n minus k minus 1 T square by sigma square. So what is this? So this we all know follows chi square k minus 1. We know that this follows chi square n minus k minus 1. What do we know? We know that these two are independent, right? S square and T square are independent. We know. S square and T square are independent. So if that is the case, then what is the property of chi-square random variables? Can you add chi-square random variables and get a chi-square random variable again?
Yes, sir.
Why? That is because gamma random variable. Correct. Gamma additivity is there. So what is the density of W2 then? Chi-square k minus 1 plus n minus k minus 1, which implies that W2 has a density which is chi-square. K gets cancelled, n minus 2. Correct. Is that okay? Is that fine?
Yes.
So now you get hang of how you are going to do, how you are going to tackle these type of problems. Is that okay? So similarly, you can look at other problems in the assignment. the problems which are based on the sampling density, sampling distributions, basically this is what you have to understand. So in sampling distributions, if you have to address some problems, these are the rules that you will always remember, right? So these are the rules. If you have a normal density, you normalize it to get standard normal. How do you do that? X minus mu divided by sigma. If you have n independent identically distributed standard normal random variables, then sum of squares of those is chi-square. How do you get t from chi-square and standard normal? You have to look at. How do you get f from chi-square? You have to look at. Everywhere you have to make sure that independence is really important. U and V are independent. Independence of these random variables that are there, this is really very important. Only because of independence you are able to have these additive type of results and these other results, right? So here independence is important in gamma, because you can add independent gamma random variables and get a gamma random variable. Here the independence is important in T, because you wanted to write down that joint density as product of marginals. That's what you wrote down, right? So that's why independent of U and V was important, and same reason why independence of U and V was important in the F distribution. Okay, so these are the type of things that you will have to remember, and this is how you will try to solve the problems. Okay, so I have uploaded assignment 8 that was circulated by Professor Somesh Kumar. So that assignment is already been uploaded. After the class, I'll upload the lecture notes for today, and I think next Monday you have exam, right? So
Yes.
all the best for the exam. Try to solve the problems in the assignments. I think assignment 6 and 7 solutions are also available now, and assignment 8 solution probably will be made available in a couple of days. Try to solve all the problems. The problems mainly are based on joint densities, transformation of random variables, central limit theorem, so the approximate calculation of probabilities, and these sampling distributions, right? So these are the main areas on which the problems are based, and I think the exam will also be based on that. So like every time there will be that instruction sheet with syllabus and everything that will be circulated to you about the class test. So this is basically the syllabus. Okay, so all the best for the exam next week on Monday. So after the exam, Tuesday is still a working day and a class day. So we will meet on Tuesday. Maybe instead of 8 to 10, we'll meet from 9 to 10. Okay. So next Tuesday between 9 to 10, we will meet. We'll discuss whatever things are important to be discussed. Okay. So we'll stop at this point of time, and all the best for your exam. Okay. Yes, Priyanshu, go ahead.
Sir, means did you cover that approximating gamma